Today we're going to finish up our railroad section and do a little talk about the geometric pieces of railroad design, and then we're going to move into kind of a newer category, which is connected vehicles, and a little bit about autonomous vehicles as well, and what the difference between those are, which is a cutting edge kind of piece of transportation engineering that's come up here in the last few years. So back to railroad design, we were last time we talked about some of the structure, some of the how the rail is specified by weight, and also by looking at all the track structures and what the rail sits on the ties and the ties on the ballast and so forth, and just how the track bed is constructed, kind of similar to how the road bed is constructed in a cross-section study we've looked at before. Now we're going to move into the horizontal piece of it, which it's fairly familiar from what we did with cars and with roads and highways. For that, the biggest difference in horizontal curvature, right, so alignment, we would call this, right? This is plan view looking down on, this would be the track in this case. We still had the point of curvature, point of tangent, or PI. That hasn't changed. The difference in highway is we measure the length of the curve along the curve itself, along the arc of the curve. And so in highways, that's how we would measure it. In railroads, we break it into chords, and the chord is just little straight sections. And so we'll break this arc piece, this curve, into 100-foot long straight sections, and sometimes little pieces of that. So here is that arc length. In railroads, it'd be this cyan color, this blue color here. We're going to break that into 100-foot sections through that, and that's going to be how we define a curve, and then we measure it in 100-foot straight sections. And so we kind of rasterize a nice smooth arc, and we break it into 100-foot long sections, and that's how we measure the length of the curve for that. And there's reasons they did it this way back when they were big on building a lot of new railroads, late 1800s, would be in the U.S. when they were doing this. They were laying all this out in the field, oftentimes, a few weeks before the track laying crew got there. They just took off, right? And the Great Northern Route was kind of famous for that. Their surveys group and their engineers were, some days, some weeks ahead of the rest of the road building crews they came through, and they would look for routes across the mountains and through the west, and look at different ones, but they would lay it out in the field, and it was pretty common to lay these things out in the field. Well, the way they did it was on these arcs, on these curves, they had 100-foot long tape, and they would or string, and they would just lay it out that way. And that's exactly how they would lay these out. Is they had two guys and one on each end of this 100-foot long piece, and they would just leapfrog across and lay these things out. If somebody else was back here with a transit, tell them what angle to move each time. And so that's where this came from, and it was an easy way to lay this out in the field versus the more theoretical version of measuring along the arc. Right? So that's a big difference in horizontal curves. If you ever work on a railroad project, just remember that most design software like Civil 3D, you can toggle it to do arc chord definition for curve length, and so you'll make sure you want to do that before you start designing for the railroad, right? So you make sure you get the lengths right. Your client will not be happy if you do it otherwise. Here's from another book how they described it. D is this angle in interior here, and if this is a 100-foot arc, a degree of curve D in road terms, which we don't use a lot anymore, but they used to. That would be your degree of curve. That's how many degrees of change your vehicle did, the angle your vehicle is pointed at, how many degrees it changed as it goes through a 100-foot arc. In railroads, it's by 100-foot chord. Here's this chord in here. That's what you're measuring by now, not the arc, by the chord. And so this is that degree of curve. So the definitions are slightly different for degree of curve based on the arc versus a chord length one. This is what the definition is for horizontal curves. If you know what your degree of curve is, and in railroads, that's how they like to define curves. And so you'll say it's a 1 degree curve or a 2 degree curve or a 1 degree 30-second or 30-minute curve and so forth, which means how much change in direction do you have every 100 feet of chord. Right, through that. So you ran your piece of string, your 100-foot piece of string across here, and from this end to that end, how much of a change in angle of bearing would your train have as it goes through that 100 foot of chord through that. So here's our definitions. Take d over 2, that's the degree of curve, divided by 2, sine of that, and all of that is in the denominator with 50 in the numerator. That'll give you your radius if you wanted to calculate the radius. Back to here. If you know what your total change in direction is, and then divide it by the length of the curve, that pops out exactly at what your degree of curve is, right? See, pretty simple equation, really handy for laying things out in the field in a hurry. And this t distance from your pi, your intersection point, back to your point of curve, it can be calculated as the radius times the tangent of delta over 2 for that. So that's our curve definitions, equations for railroad curves. The other thing to think of in horizontal curves for railroads is they always have spirals. On a mainline track, railroad piece, it's always going to have spirals, right? Now we're going to talk about if you have a we call a turnout where you've got, it looks like a curve as well coming off of a tangent piece, right? It's a little different, but on mainline tracks, you're always going to have spirals either side of the main curve, right? And what this is, the spirals are here in the red. So this is tangent to spiral, spiral to curve, and then curve to spiral, and down here spiral to tangent again. That's your ST point. So these red portions are spirals. This is your circular arc. So this would be your standard curve. All right. In highways, we often don't use spirals. We need them in most cases. Our roads are general enough and our lanes are wide enough. A railroad on trains, they'd have to have a spiral on either end to ease them into the curve and then ease them back out. When you're driving, you do that with your steering wheel. You go from pointing straight up to, you move it to the side to whatever angle. Once you're in the full curve, you hold it at that same angle all the way through the curve, and then you're easing the wheel back up to the straightforward position on the other side. That automatically creates a spiral for your vehicle. Train, you have to build it into the track to ease the trains into the curve and back out of it. Again, so just to keep that in section, these are the spiral sections are in the red. Again, the arc section, standard straight curve, is right here in blue. Right. So another thing to keep in mind, we won't get into the fancy equations for spirals and how to calculate all that stuff. In this, just keep in mind we do have to put spirals in to the curves for trains, which we don't have to do for roads. On that. The other thing we look at it in curves are also just like roads. We have super elevation, right? So we have to tilt the trains to help them get around the curve, so they can go faster around the curve, and it balances the forces, right? The centrifugal force, which is pushing this train out, is trying to be balanced by, because you tilted it, there's a gravitational force now that's off the center of gravity a little bit to one side or the other of the center line of that train. I don't know if it's on the inside, hopefully. Right, depends on how fast they're going, where that resultant force ends up through that, but that will allow the train to go through these curves faster. And this is Amtrak trains in I think this is a Philadelphia commuter train, SEPTA, on the Northeast Corridor, which is, you can tell because it's electrified. It's one of the few electrified lines left in the U.S. besides the South Shore, right, in the Illinois Central line. For that. So these are all passenger trains, and you can see the tilt on the trains as they come through the curve. Through that. Actually, this one's going away, this one's coming towards us, that's coming towards us. Through there, you can calculate the maximum speed you can go on a curve by, if you know how much super elevation you've got, plus 3, divided by 0.0007 times the degree of curve. So there's our degree of curve term again. All right. In railroads, the way they measure super elevation, remember in roads, we do it in percentage. We'll say it's a 2% super or 6% super. All right. 8% would be the max in Indiana. That's always a test question. So in railroads, we measure it by inches. And so here's how the device they use for it. It's a little hard to see, maybe in here blends into that color, but there's a level on this. And so you set this up, and then you crank up the low end, whichever rail is lower, you crank up this measuring device until the level bubble up here shows that you're perfectly level, which would be this bar is level. And then this unit it's measuring is the distance from the lower rail up to that which would be the level that the higher rail sits on. For there, and they measure it in inches, right? They measure super elevation in inches, and in this case, we're saying that there's 3 inches of unbalanced super elevation, which I'm going to tell you what that is here in a second. So just keep that in mind. And that's standard. That's pretty standard for US to have 3 inches unbalanced, to allow up to 3 inches unbalanced super elevation. The actual super elevation you read on a device like this, the actual difference between the high rail and the low rail is E sub A for that. So what is underbalanced, overbalanced, and equilibrium look like? This is what it looks like. Okay, so here's your train car, right? If it's overbalanced, you've tilted the tracks a little too much, right? Equilibrium, all right, let's start there. Equilibrium means you've tilted the tracks to perfectly match the amount of, let's say the X component of the gravity vector here is just enough to balance the centrifugal force. And so if you're riding on that train, you won't feel the curve at all. Right, you'll be perfectly balanced. Your cup will not try to slide off the table one direction or the other, right? No marble's not going to roll to one side or the other of the car. You're perfectly balanced. And that is, you've tilted the train car just enough that the resultant, the resultant vector is going directly through the center of the car. And through starting at the center of gravity, it passes right along the center line of the car. And so the vector coming from the gravity versus centrifugal force is exactly balanced, right? Overbalance is that you tilted too far, and you'll actually, at whatever speed you're going, you'll feel a tendency to drift to the inside, right? If you have a marble on a table in here, it's going to roll to the left. You've overbalanced. You've tilted the car a little bit too far for that speed. All right. Now, if you went a little faster, it might be perfectly equilibrium. So that's interesting piece, right? Forward there. So whether you're in equilibrium or not depends on what speed you're going. All right. And then underbalanced is that you didn't tilt the car quite far enough. You didn't tilt the rails quite far enough, and you're still going to feel a force pushing you to the outside of the car, and that's underbalanced. All right, and that's we call that 3 inches of underbalance. It's okay to feel enough force as equivalent to raising one rail 3 inches higher than the other, that the unbalanced piece. If you went through that and you weren't on a curve, that whatever force you feel, that shift is okay. So we say that's 3 inches of unbalanced. And so you can be that far off. You can be 3 inches off. All right. But you don't want to be 4, because 4, the car may start to tip, right? Or it feels uncomfortable for passengers. It's so much force to the outside, right? You expect to feel a little, right? If you go around the curve, like, oh, we're going around the curve, I can feel it, right? But up to a certain limit, the limit they pick is measured in inches, and it's 3 inches. So that's our underbalanced. If we go back to this equation, that's this 3. We say, okay, that's our normal. You can have up to 3. Here's the actual super elevation. Here's the degree of curvature. That's a measure of the sharpness of the curve. All right, and that will give you your velocity, your max velocity in miles per hour, right? So this is in degrees, and this is in inches, and that's in inches. But somehow we get miles per hour out of this, right? So this 0.0007 is the conversion factor that takes care of all of that unit conversion. So this is a unit conversion factor. Right? So that's what that's in there for. So yes, the units are weird. Just trust me, it comes out in miles per hour. Okay, because this thing is handling it. Okay, so that's how railroads talk about their super elevation, right? So vertical alignment, keep in mind, mainline railroads, this is an old steam engine from England, but mainline railroads typically stay below 1%. Right. So in highways, what's our max? What would be a normal maximum in Indiana on interstate? Right. We're not going to go over 5% on freeway here. If it's a smaller road, you might go 6 or 7%. And out in the mountains, yeah, some freeways are at 6 or 7% out in the mountains in the Rockies, but generally we keep it below 5 for truck traffic to handle, and it's safer. Railroads can't handle, think about how much weight is being pulled by a single locomotive, right? They're very efficient, but they don't have excess capacity. They don't have a lot of extra horsepower laying around that they can just motor right up these grades. And it's a steel wheel on a steel rail. Traction's a bit of an issue, can be. They do things to improve that, but still, to keep things efficient, you limit your grades to 1% on the mainline track, which are this would be like your arterials in the railroad world, right? You're going to limit that to 1%. You try to have as many curves or as few curves as possible. 0 is the best, right? A turnout, we're going to talk about what turnouts are. You only do that on straightaways, on the tangent track, right? And if you've got vertical curves, you need a nice long tangent in between, or longest tangent as you can in between, because as long as these trains are, if they're going through multiple curves, if one part, the front part of the train is in one curve and the back part of the train is in another curve, that is a huge need of extra horsepower by the locomotives, which they may or may not have, right? You can stall a train out on tracks. It happens. Right? If you check YouTube, people show pictures now and then of this train stalled and before they could get it going again. So if you're a real geek, you can do that, right? Vertical curves, it's the same idea, right? You've got an incoming grade, you've got an outgoing grade for vertical curves. They're parabolic, exactly like they are in highways, right? And in highways, the way we limited curve distance or length was by sight distance, right? We needed to have a gentle enough curve, which means it's going to be longer, that you can safely see over the top of it in a crest situation, or it's safely illuminated by headlights in a sag situation. In railroads, it's all about not changing too fast. We have to be very gentle, right? It's almost like walking on eggshells, right? Very gentle grades, not above 1% on either side, A or B there. And we don't want to change real fast going through this. And this is the equation we use in railroads to determine the minimum length of curve. Trains don't care about stopping sight distance. Interesting, right? What is the stopping sight distance of a train? You think, right? The stopping distance of a train is on the order of a mile, right? To get a train to stop, it's on the order of a mile. Oh, there was a really good, there was a video in Elkhart County. A limousine got stuck on the tracks and got smacked by a train. Train saw it, hit the brakes. It wasn't going real fast to start with, but it drugged that limo. It was perfectly balanced on the rails. It drug it like almost half a mile, and it was still just sitting there right in front of the train when the train finally stopped. I need to find that video from that. It's only about 5 or 6 years ago. There in Goshen. So it takes a long time to stop a train. If if a car crosses right in front of them and they want to slam on the brakes, there's no way they're going to stop. They don't even try to calculate a stopping sight distance for a train. And it's going to depend on how many cars you have behind you, if you're going downhill, if they're heavily loaded, so forth and so on. So the length of a curve, required minimum length of a curve for trains on vertical is only dependent on now we're using D as the algebraic change in grade. So the change in grade here, your velocity, and then some conversion factor. So you're converting degrees and miles per hour, and you're going to get feet out of this. All right. So this is a conversion factor. It's 2.15 for there. And then you're going to divide by some maximum acceleration grade, which is roughly equivalent to how fast a rate of a change do you want. And so for freight, you only want 0.1 feet per second squared as our rate of change down here. Where for passenger trains it's 0.6. So the passenger trains can handle it better. Passenger trains have a lot more power per train. Freight trains are, if they're being run efficiently, they don't have much extra. Right? They've got it exactly matched. Okay, in the mountains they'll add locomotives on, but they still don't have much extra. Out in the flatlands they'll keep it down to 2 or 3 if they can. And there's not much extra. So they're going to make it really gentle. So this 0.1, and it makes really long curves. Trains have really long grades and really long curves for that. All right, well, I said I'd tell you what a turnout is. Here's what a turnout is if this is our mainline track and we want to have a side track coming off of it, we call that a turnout, right? It's just like an off-ramp for trains. You've got a switch. Back here, the switch slides this rail over against that one, and so the flange of the train catches this rail and follows it this way. It comes across here, it crosses this rail, and it keeps on going for that. This is bent rails. It's obviously curved through there. Here's the switch. All right, this switch moves this bar and that bar at the same time, and so when it slides over, the flange catches that, and then this doesn't catch this flange, and this wheel follows that rail around. And where this, I'd say, inside rail crosses what's the new outside rail, we call that a frog, point of frog over there. The odd term, I know. But apparently they thought if you looked at this from straight above, it looks like a squashed frog. That was the story I heard, why they call it that. That could be wrong. Right. In turnouts, we number them. And so a number 10 turnout has a certain angle. So it's a 5-degree departure angle. Right. So if this is our straightaway and you have a turnout, we'd have like a 5-degree, 43-minute, and 29-second departure angle. I don't know why it's such a weird number, but that's what it is. For a number 10 turnout. And these are all standardized numbers. You can look it up in the book of standards and see exactly how to lay out a number 10 turnout, right? A number 20 turnout has a much lower angle for that. And where would you use a number 20 turnout, right? If you wanted to have a turnout on a higher speed track, right? You can go faster at this lower angle turnout. Number 10, you're going to have to go, below a certain speed to safely, follow that curve around and exit. The mainline track for that. So just remember that the higher the number of turnout, the more gentle it is, right? And there's some really high numbers, like high-speed trains, not so much here in the U.S., but in other places, I think there's a 30 and a 40 turnout, could be even higher for that. Right now, if you ever ride Amtrak anywhere, you can tell when we're switching tracks because the train's going slower. We've slowed down. Mainline is often in this number 10 and number 20 would be common, right, for that. And about the max speed you're going to do one of these turnouts is 30 miles per hour, something like that. And that's a number 20. I think it's even lower for the number 10. So those are turnouts. So that ends our railroad discussion. I'm going to just leave these here and let you, in the interest of time, follow these links if you want. Talking about connected and autonomous vehicles, been in the news a lot. You guys have probably heard about it a bit. This is some cool videos that Tesla produced showing how, excuse me, their autonomous cars operate, and it kind of shows you what the car is seeing as they drive. So it's kind of cool. And they, obviously they handpicked probably a nice route that wasn't that hard for it. And maybe they took 2 or 3 tries to get a really nice run. But so it looks awesome. But Tesla still doesn't have full autonomous mode, and it's got assisted driving, even though they call it autonomous. It's not quite, definitely not yet for them. It's getting closer all the time. And then this is a TED Talk, a couple links here that talk about if you've got driverless vehicles, how could that change how we do transportation, right? If you don't have a driver, Uber was trying to develop their own driverless cars because they thought that was the future. They're a rideshare company, but they'd prefer not to have a driver, and that the car just itself comes and gets you and takes you places, right? And people say, well, if you, as a family, right, you own one car, but it's autonomous, right? So it takes one of the parents to work, and then it comes back and picks the kids up and takes them to school. Right, assuming it's not that far away, and it doesn't have to wait in the parking lot. Right, so you can get by with fewer cars, and your 13-year-old kid can take the car and go over to see their friends if they wanted to, or go shopping or something. They don't even need your parents anymore. Right, they can just summon the car, and the car can drive them there. So it's interesting pieces about where driverless cars might fit in. Right, taxi services was a big one. Too. So how would that change the transportation landscape and society to some degree as we know it if we truly had driverless cars that didn't need us for that? All right, the next piece was a talk I gave a while back about doing a connected vehicle demo project up in Elkhart, near Elkhart, city of Elkhart in Elkhart County, Indiana. And so this is coming from that a little bit, but I thought, this you hear a lot of buzz, a lot of talk about connected vehicles, connected and autonomous. And sometimes people, I think, lay people confuse those a little bit for that. So this kind of gets a heads up about what the difference is, and then shows you what connected vehicles might be able to do if we had more devices installed in the world that could use it. Right, for that. So here's an interesting picture. Are these connected vehicles? Right. So there's a lot of buzz about connected vehicles, and everyone thinks it sounds great, but not a lot of people really know what it is. I think outside of maybe our industry, it's easy to confuse that. So this is not. These are connected. That's not what we mean when we say connected vehicles. All right, so we're going to go through a little primer on this. Is that how the British say it? Or a little primer on what connected and autonomous vehicles are. All right, and this is a USDOT. They promoted connected vehicles a lot. And so everyone borrows these same graphics from USDOT. Thanks, USDOT. Like a lot of companies that make the stuff are borrowing these graphics because, hey, you can, they're the government. Stuff's not copyrighted. So this is connected vehicles. Everything's talking to each other, right? That's kind of connected vehicles. Oh, I foreshadowed it. All right, so autonomous vehicles drive themselves, and they may or may not be a connected vehicle, right? The Tesla, if you follow those links from Vimeo there, those are not connected vehicles. They weren't talking to any other car near them, and they weren't talking to the traffic signals or infrastructure, as we generally call it. Right? They were not connected, but that car in particular was autonomous. It could drive itself, at least to some degree, right? And they're getting better. They just aren't. They're not at 90% even yet for doing a good job to do that. So they're autonomous, and in that case, they were not connected. Right? Connected is talking to. It's talking to the infrastructure or other vehicles on the road. Right? You can be a connected vehicle and not be autonomous. In fact, that's the only kind of really of connected vehicles we have right now, are non-autonomous connected vehicles. But you can get information from the infrastructure. The traffic signal can tell you when it's about to turn red or about to turn green. Well, that's kind of handy, right? And you can see where that would actually help out autonomous vehicles if they knew what the traffic signals were planning to do. They didn't have to use visual cues to get that. All right, a 1993 Geo Metro. Anybody seen one of these? If you live in California, there may be still some out there. They did not handle rust well in the salt world of Indiana, so there's not many. I don't know the last time I saw a Metro in Indiana, right? Pretty simple car, very basic. It was 3-cylinder. It had no power steering, no power brakes. Everything was manual. But when your entire car weighs 1,200 pounds, you don't need power steering and power brakes. Super simple, right? How do I know about Metros? Because I own 2 of these. And yes, I got lots of jokes about, do you take the front seat out and sit in the back? Yeah, okay, maybe I did. So anyway, super efficient. You could get 50 miles per gallon if you really did it right with these. And this is a 1993. Right? I think I owned 193 and 194. So a multi-owner. Used to call it the Metro a snowcat because it is front-wheel drive. It would go through the snow fine. So is it connected and is it autonomous? What do you think? Right? Probably not connected. Definitely not autonomous. All right, next vehicle, airport people mover. Right? I was writing this presentation on a trip back from overseas, and so I was flying through Dallas, Fort Worth, and lo and behold, here comes the airport people mover. Right? Is there anybody driving the people mover? Nope. Right? They are completely autonomous, and they're probably connected. They know where they're at, and they're talking to the infrastructure. So they'll know when they get to the station, and they'll stop there and open their doors. Right? And they know what the next stop is. So in probably not a very complicated environment because it's on a fixed track and it's so forth and so on, but it probably is both connected and autonomous. Right? There's nobody driving it. It's definitely autonomous. And being on a train, it doesn't need anybody to steer, so you got that. So it's a simpler environment, but it could be both, right? And same trip, same airport. Here's an American plane taking off, and is it connected and is it autonomous? What do you think? Right? We had a car, we had a train, now we're having airplanes. Look at this. How inclusive can we get? So we've got this. Does it know where other aircraft are, and does it know something about where it's at? Yeah, it does. They have pretty good systems on them now. These modern airplanes. They definitely know where other aircraft are. They can track where other planes are, and they know where they are. And as we just talked about, with instrument flight rules, planes get glide slope and directions to land and stuff from actual infrastructure at the airport. So they are kind of connected. Maybe not as much as we hope cars will be, right? How about autonomous? Can an airplane drive itself? Answer is yes, right? There's some jokes about pilots basically just sitting up there drinking coffee all day because the plane's flying itself, right? Once they take off, they put it in autopilot. It does it all itself. You know, they don't take it off autopilot. A plane can land itself on autopilot. Did you know that? I didn't either until recently. A friend of mine is a pilot for United now. But he said, yeah, they can land themselves. He says you can tell because they're bumpier. He likes to think that he has soft landings versus the autopilot having harder landings. I'm like, well, that scares me a little that these pilots are letting these planes land themselves. So, autonomous, yeah, kind of is. Now, maybe not in the taxiways and coming to the ramp, but a lot of times it is. Okay, how about the standard Elkhart County vehicle? A little joke there. All right, a lot of Amish people living in Elkhart County. And so here's a horse and buggy. And this is actually, this is just outside of Elkhart. The woods here is Elkhart County. This is Marshall County, in case you want to know. This is US 6 over there. So this is Tina, the horse, and my friend Johnny. His parents are Amish. He's no longer. And so he would let me take pictures of him. So that's the plus there, right? So we were testing what sight distance you'd need as a buggy driver versus the sight distance we have in a green book related to cars. All right, so is this connected and autonomous? Well, horses aren't stupid. Depends on the horse, but they generally aren't stupid. They kind of can tell what's going on around them. I don't know if the infrastructure is talking back to them, but maybe a little bit. They definitely can be autonomous, though, right? There's a lot of jokes going around about, people drink too much and their horse knows the way home, and they just show up in the barnyard, and they didn't remember how they got there, but the horse knew and got them home safe, right? Through that. So horses can definitely be autonomous to a degree, sometimes more autonomous than you want them to be. They don't do exactly what you told them to or wanted them to for that. So yeah, maybe a little bit of both, mostly more autonomous, I'd say, for that. All right. So here's a standard. This is a Trailblazer. So if we just had a Trailblazer, right? Is it connected and is it autonomous? Right, this is probably a 2003 Blazer. And the answer is it's definitely not autonomous. It's way too old for that. It wasn't even a thought back then. But is it connected? Right, well, it can be. It can be if you have the right phone app. Right, and so the connected part is that the driver is getting information from the infrastructure and can make a decision based on that. So there's your connected piece. So yeah, they can be. Right, the solution here is that none of these vehicles could ever officially be connected on their own, right? The airplane probably could, the people mover is, but you can connect the driver. And even in a buggy, he can get detailed information about what the traffic signal is doing. If you want to do. Now, the horse probably isn't using the phone app, but the driver would be, right, for that. So the drivers can be connected. For that. And a little bit definitions here. There's two modes in connected vehicles. One is that your car is talking to infrastructure, traffic signals. It's almost always just traffic signals. Or the car is talking to other cars on the road. And so it's called V2I or V2V, if you want to use cool federal highway terms like that in jargon for that. The main one that's really getting used is vehicle to infrastructure, because that's the one you can really count on. How do you know if any other vehicle has stuff installed and it's on using the same system you're using? Right, there's supposed to be a standardized one. This is a little bit further away. All right, for that. So originally you were going to install little, looks like Wi-Fi, outdoor Wi-Fi radios on all the traffic signal poles and in your cars. And you would be broadcasting as you drive down the road, and every traffic signal you come up on is broadcasting, and you pick up that signal and you say, oh, this signal's about to turn red. Nope, it's about to turn green. And so forth. And that was the original envisioned version of this, is every device has their own little radio that's broadcasting on it. And they literally are made by the same people who make Wi-Fi routers and stuff. Right, for that. The problem is this is a lot of stuff to install out in the field. So, INDOT has over 2,000 traffic signals they maintain in the state of Indiana. They had to buy a wireless radio for every single one of those, and that's a lot of money and a lot of maintenance. Right, these things aren't they're a little spotty, right? You have to come out and fix them, and so forth. It's just a lot more for a government agency to have to maintain. Right, for that, it's moving. Pretty much the whole industry, I think, is starting to believe the world is going to head for cell service. And this is what we're going to see. This installation here is this example. And what this does is there is no radio at the intersection, but your your traffic signal at the intersection has a link to the internet. It's broadcasting what it's doing to a special service, who then broadcasts it back to phone apps using that person's cellular data plan. Right. So your cell service signal, that's how you're getting that back in the car. And that's what this setup was. And there's not that much lag. Even though the server's in Texas somewhere, it went from Elkhart to Texas over the internet, and then it got routed back to that phone device using cell service as it gets there. Right. So that's the difference. For that, wireless radios are still officially supported by the feds, and originally they were going to push it, as that's the way it has to be. Almost everybody is seeing that the cell service way is going to be a lot simpler in the end, especially for the agencies who have to maintain these things, right? And the thing is, all you need now is a smartphone. That's really all you need. You have to load an app, and then you're ready to go. And most cars nowadays have their own cell radios in them, right? Any nicer car, I guess mine does not, but any nicer car has a cell modem in it often these days. And that's all you had to add, and they're fairly cheap, right? This is DSRC. You got a little radio here. Looks like the external Wi-Fi routers like on campus. As the vehicle comes up, it's got a little antenna. It's got a processing unit. It drives up, and this traffic signal controller is sending information up to here, broadcast it. Now you know in the car, or the car knows what's going on up here at the signal. Okay. If you're doing the cellular version, the cabinet is somehow getting its signal up to a server. That server then that you link to with your app is sending that data down to you in the vehicle or your vehicle itself. All right, so Howell Lee, my friend down at Purdue, did these slides a while back, and he let me borrow these because he did a nice job on showing what the difference are. All right, and a little more details. This is what the DSRC, the radio version, looks like. Here's the traffic signal controller. Here's the little roadside unit. Yeah, the big Wi-Fi router. Here's the unit that sits in the car, and it decodes the signals as it comes in and lets you know what's going on, or it tells the car what's going on. Here's what the roadside unit looks like. It's got the big antennas. It's got a GPS antenna to make sure it knows exactly where it's at. And it locks the time in that way. We use that a lot of time to synchronize time for that. Didn't know if you knew that or not, but that's a major use of GPS, is being able to synchronize time as well. This is the onboard unit. Okay, it's also got a GPS and a radio antenna. The GPS, again, is making sure when the signal says, hey, it's 4:02 blah 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 p.m., you want to make sure you're reading that right. And like, okay, yeah, I think I'm on the same time. Yep, here we come. And it's all in universal time, so you don't have to worry about conversions. There's two big corridors in Indiana, one in Greenwood and one in West Lafayette, that are using DSRC. And the INDOT, State Department of Transportation, is testing these out with the help of some researchers. So that's why they've got those. The 4G cellular one, that's the link there. Here's all the traffic signals in Elkhart County, and we did one test one up here at 6 and 10, County Road 6, County Road 10. So if you're from Elkhart County, you might know where that is. There's a gas station there now. For that, this is what it looks like. There's a device. This was by Applied Information, is the manufacturer we were using. It depends on your manufacturer. This is the brain system, right? That's collecting data out of the traffic signal, and then it uploads it to a server down in Texas, in this case. Here's a bunch of wiring. It took a lot of wiring to do that. They've got a cell modem link for it, because this traffic signal did not have its own internet service. And here's a GPS puck again to identify the exact location and keep the time in sync with everything else around it. Here's Dave wiring these things in. And there's a lot of wires. That's all this is showing. There's a lot of wires. Once you get it in the software side, you set up, and this is what the intersection looks like. Gas station's here now, wasn't it? This picture was taken. You set up each of these lines, and each of these data points is showing a different movement. This would be like your eastbound through movement. The lime colored one here would be your eastbound left turn. And so you delineate where the center of the lane is, and then you tell it what movement that is. And here's the color code for what each of these movements are. And then as you're driving along, your smartphone in your car says, well, you're in this lane. You need to know what the through traffic signal head is telling you. which movement you're in. Here's how it's set up. Here's your lat and lunge, which phase it's all linked to, and so forth. Here's a blow up of that. Here's that through movement. All right, and here's the left turn lane defined in that area. Right, so if it thinks your car is on this line, it's going to show you what the left turn light's doing. If it thinks your car is on this line, it's going to show you what the through movement is doing through that. And it's a phone app. They call it Travel Safely. You just log in, and then it'll show you as you go through, right? And it's pushed out to that. It could be a tablet as well. It's just an Android system. I think they actually have it on iOS too. Here's permissive left. Hopefully these videos will come across kind of okay in that. So here it is, and it's showing we've got red, and it is red up here. I don't know if you can see that. It is red. Okay, it knows we're in the left lane, and it says it's more than 10 seconds before it turns green. They don't want to tell you exactly how many seconds until green because they think maybe you'll just look at your phone and you won't actually look at the signal. Now it says get ready. It actually has a voice command. You can't hear it, and you can barely see it. There's a little green arrow. Yep, it's showing you exactly what you should have seen as you went through. So that's the connected vehicle thing. That's kind of cool, right? That's permissive left. Here's through on green. So if you're approaching and it's still green, you don't have to stop. Right? It tells you, here's a green arrow, and you have the green ball indicator. There's actually construction that day, and whoosh, right through. And it turned red about the time we got through. That's cool. It can also tell you if there's construction zone coming up. Here is arriving, but it's red. It's going to warn you. It just turned yellow. Now it's red. There's a little voice command that comes on and tells you prepare to stop. So there. And it also will warn you about pedestrians. And so if a pedestrian has the same smartphone app on their phone and they walk in front of your car or near it, it'll warn you about a pedestrian. Yeah, if you saw the little flashing decal there for that. If you, I guess, yeah, you won't, the PDF won't be able to show these in the notes. But so that's a pedestrian. It'll also warn you if you're about to hit the back of a car. This car, county car, stops in front of us. It warns you. Emergency brake. Okay, so if you're coming in too fast on a red light, it's going to warn you. It beeps at you and everything, right? Through that and flashes. All right, so that's what connected vehicles can do. You can also get it installed in the car itself, and so Ford and working with this company, and you can get right on your screen, your dashboard through that. And it looks just like the phone app did, but now the car itself has it built in, so you don't have to have your phone out when it's doing it. And so there you go. Okay, that does it for today's lectures. A little taste of what connected vehicles could look like for that, as well as finishing off railroads. Next time we'll do review for the final.